All right, so with ChemActivity number 17, what we're looking at what a molecule looks like in three-dimensional space. We're taking into consideration any lone pairs of electrons that the central atom has around it, as well as basically the overall bonding pairs, everything that surrounds a central atom. So we're all doing this kind of molecular geometry analysis from the perspective of our central atom. So I think that the best thing to do is to start out by looking at a couple of molecules. Now, in your ChemActivity number 17, you looked at three specific molecules. You look at water, you look at ammonia, and you look at methane. Now, you look at these because there are some similarities and there are some differences. What I'm going to do is I'm going to start out with methane. Methane has a formula of CH4. Our central atom is carbon, and we have a hydrogen in each direction. Now, one of the things that's really important to keep in perspective with this is that this is all in three dimensions. So the placement of these hydrogens is not simply 90 degrees from one another. It's not like one is to the right, one is to the left, one's up, one's down, these hydrogens that is. Instead, these hydrogens are positioned with respect to, well, one can be coming out of the page and one is going back into the page. So ultimately, what that means is that the angle measurement between these bonds is 109.45 degrees. So each one of these bonds has the exact same angle measurement. In addition to that, it's important to appreciate and acknowledge that, or kind of appreciate the overall geometry for this. Since these bonds are 109.45 degrees, the terminology for this is considered a tetrahedral molecule. And we're going to get into these geometries in just a little bit, but a tetrahedral molecule, that's a central atom with basically four bonding pairs surrounding it. Now, in addition to that, it's also important to think about, well, what did we talk about previously? Previously, what we were talking about was hybridization of orbitals. What is the hybridization of this carbon? Well, this carbon is sp3 hybridized. So one way that you could think about that is, well, it has four things surrounding it. So it's S plus P plus P plus P. Well, that's three P orbitals and one S orbital, so it's sp3 hybridized. Okay, so our next molecule is ammonia. Ammonia has a molecular formula of NH3. Now, when you draw ammonia, it's kind of interesting because of the fact that you have 1, 2, 3 hydrogens coming off of that central nitrogen. You also have a lone pair of electrons. One of the things that I've talked about in lecture is that what is the space that these electrons are occupying, and what is the kind of attractive forces that are kind of keeping these electrons in check. Well, if we think about these electrons right here, where I draw the star, well, they are attracted to this nuclei right here, this hydrogen nuclei and this nitrogen nuclei. Now, that's not quite the same story as for something like these two lone pairs of this lone pair of electrons, which I've now drawn a star behind. This lone pair of electrons, well, they're not going to occupy the same space as a pair of electrons within a bond, because of the fact that these two electrons, they're only attracted to one nuclei. And so what that means is that they're going to fill a space that's a little bit larger. And that's not really drawn particularly well, but just imagine that that's a balloon. And what these electrons are going to be doing ultimately is they're going to be pushing any other electron pairs away from them. Okay, so this right here has a slightly different geometry. Now, the bond angles between these hydrogens are approximately 107 degrees. So there is the same number of things that are surrounding the central atom, but what this lone pair of electrons is doing is kind of exerting its force. It's pushing those electrons away. So we have a 107 degree bond angle measure there. Now, the hybridization of this, well, one way that you can think about hybridization is, well, what are the number of things that are surrounding it? And so if we think about, we have a total of 3 things surrounding our central atom. And so again, we want to count up those three things, or I'm sorry, we have four things surrounding it. We have a lone pair of electrons and 3 hydrogen atoms. So this is S plus P plus P plus P. This is also sp3 hybridized. Okay, so the geometry of this is similar to ammonia, but it's going to be a little bit different. This is considered a bent molecule. So if you would, I'm sorry, this is not a bent molecule. I apologize for that. This is not bent. This is a tetrahedral molecule because it has 4 things surrounding it, but more specifically, this is known as a trigonal planar, due to the fact that our bond angle is less than that 109.45. So we're looking at 170-degree bond angles. Now, if we look at water, well, water has a formula of H2O. What this consists of is a central hydrogen, or a central oxygen with 2 hydrogen molecules coming off, or 2 hydrogen atoms coming off of it. Now, again, we're presented with that scenario where we have 2 lone pairs of electrons. Well, in this case, I'm sorry, we have lone pairs of electrons and we have 2 lone pairs of electrons. Well, these are going to be pushing not only down on these oxygen-hydrogen bonds, but these 2 lone pairs of electrons are going to be repelling one another. Therefore, this is a molecule that will ultimately be considered bent. The bond angles here between these hydrogens are going to be 105 degrees. Now, what we have there is an example of a bent molecule. Our bond angles are 105 degrees, and in addition to that, we need to be aware of the hybridization of water. This is an sp3 hybridized molecule, okay, or it has hybrid orbitals there. Okay, so this is just kind of a way of looking at 3 different molecules and different components in play. So these bond angles, as we increase the number of lone pairs of electrons or non-bonding pairs of electrons, our bond angle is going to be decreasing. We went from 109.45 to 107, subsequently to 105 whenever we were looking at water. Now what we're going to do, so we want to look at some of the shapes of our molecules. So the first one that we want to look at is a linear molecule. A linear molecule kind of makes the most sense because it's just going to be a straight line. So I think a good example of this is CO2. There are any number of other examples that you could come up with, for instance, HCN, if you wanted to look at something a little bit different. The geometries of these 2 molecules is actually going to be identical. In addition to that, the bond angles of these are going to be identical, as is the hybridization. So in both cases, these have bond angles of 180 degrees and hybridizations of sp. Okay. Now, if we look at HCN, for instance, what that looks like is this. We have a triple bond between our carbon and our nitrogen. That makes this a 100. The bond angle between here and here is 180 degrees, as is the bond angle between here and here. So that's 180 degrees. CO2 is carbon, oxygen on each side. Again, bond angles of 180 degrees. Okay, so that's a good example of a linear molecule. Next up is a trigonal planar molecule. So in this case, what we have is a central atom, just denoted by A, and then adjacent atoms, denoted by X, and the bond angle measurement here is 120 degrees. So what this means is that this exists on a single plane, or I'm sorry, on a 2-dimensional plane, on an X and Y axis. So these atoms can be 120 degrees away from one another. And so a good example of this would be something like B, boron, any boron containing compound, generally boron trichloride, BCl3. Now, what is the hybridization of this? Well, this has a total of 3 things surrounding it. And so this is going to be S plus P equals sp2 hybridized. Okay, so a linear molecule is going to be sp hybridized, the trigonal planar molecule is going to be sp2, the bent molecule, and bent molecules that we'll look at, H2O, for example, which we previously looked at, that's going to be an example of, and our bond angles for H2O are approximately 105 degrees. That's a degree marker there. Oxygen, hydrogen, hydrogen, lone pairs of electrons, lone pair of electrons, 105 degrees. This is an sp3 hybridized molecule, a tetrahedral molecule. That's going to have CH4 as our example. That would be our 109.45. 109.45 degrees, and again sp3 hybridized, and then trigonal pyramidal. I'm sorry, in the previous slide I referred to NH3 as a trigonal planar molecule. This is a trigonal pyramidal angle. The way that you can kind of think about that is we've got our nitrogen, and then I'm going to draw this wedge and dash representation because we've got this wedge that's coming out of the page, hydrogen going, this one right here, indicated by the star, is coming out of the page, so it's going, well, yeah, toward you. And then this other hydrogen, denoted by the other star, that one's going behind you. So we have a little bit of a pyramid here. We've got our lone pairs of our lone pair of electrons that is kind of dictating that as well. So this had a bond angle of 107 degrees. And this is also an sp3 hybridized molecule. So these are all examples of shapes of molecules, and one thing that's important to think about with respect to this is what are the number of bonding pairs and non-bonding pairs of electrons, and then what are ultimately the kind of electron domains. In this case over here we have a total of, with CO2 for instance, with CO2 we had a total of 2 bonding domains and 0 non-bonding domains. So this is simply 2 electron domains. A trigonal planar molecule is going to have 3 bonding domains and 3 electron domains. A bent molecule, well, we had 2 bonding domains and 2 non-bonding domains. In BD, no big deal, no bonding domains, and non-bonding domains. And this gives you a total of 4 electron domains. A tetrahedral molecule is going to be a grand total of 4 electron domains. Each one of those is going to be a bonding domain. And then finally, a trigonal planar molecule, we've got a total of 4 electron domains. 3 of them are bonding domains, and 1 of them is a non-bonding domain. Okay, I hope this was helpful, and I hope this gave you a little bit of a taste for what a molecule is going to look like in 3 dimensions and bond angles and everything like that. Keep in mind that a lone pair of electrons occupies a lot more space, so it's going to kind of exert its force on the bonding domains, or the bonding pairs of electrons. All right, well, thank you very much. Have a good one.